You know, it's amazing how much transformers are already doing, like powering things like ChatGPT.
Yeah.
But they could be even better. The problem is
Right.
they are such resource hogs.
Yeah.
So this paper that we're diving into today is tackling that head on with something called S2 attention,
Right.
a new approach to making them leaner and meaner,
Yes.
especially when they're dealing with these massive amounts of text.
It really is about making this incredible technology more accessible.
Right.
Because right now, the most powerful AI tools are limited to, those with massive data centers because the computational demands are just so high.
Yeah.
This paper is trying to change that.
So maybe you could just paint the picture for me a little bit.
Sure.
What is the core problem that S2 attention is trying to solve?
Imagine trying to find a single fact.
Okay.
Buried in an entire library.
Okay.
That's essentially what large language models, or LLMs, are doing all the time. It takes a ton of computing power and memory,
Right.
especially when you're dealing with those super long chunks of text. For example,
Okay.
to train a recent powerful model called Llama 2 with a context length of 4,000 tokens on 2 trillion tokens takes 23 days.
Wow.
On 2048 of the most powerful NVIDIA A100 GPUs.
Okay, so this is a huge amount of compute.
Absolutely massive. And even just serving a 70B parameter model with a 4K context length and a batch size of 32 consumes 343 gigabytes of GPU memory just for the KV cache.
Wow.
That's where it stores important information for quick access.
I mean, those numbers are just eye-popping. No wonder LLMs are so resource-intensive.
It's a challenge.
So what makes S2 attention different from previous attempts to make them more efficient?
Previous efforts often focused on sparse attention.
Okay.
The idea being that the model only pays attention to the most important parts of the text.
So almost like it's skimming.
Exactly, like reading key chapters in a book to get the gist.
Right. Okay.
While great in theory, these approaches haven't always translated into real-world speed improvements. They often didn't mesh well with the way computer hardware actually works.
So you're saying that the theory and the practice didn't always line up?
Precisely. S2 attention takes a different approach.
Okay.
One that's very aware of those hardware limitations.
Very interesting. So how does it actually work? Could you walk us through the key innovation here?
S2 attention is all about dividing and conquering.
Okay.
It cleverly splits up the task of paying attention among different parts of the model called attention heads. Each head focuses on a specific slice of the text.
Right.
But they all work together to cover the whole thing.
Okay.
It's like a team of experts.
Okay.
Each reading a chapter of a book, then coming together to share their insights.
So it's breaking down this complex task into smaller, more manageable chunks. Almost like a parallel processing approach.
Precisely. And because it's designed with hardware in mind, S2 attention achieves some seriously impressive speed-ups.
Like how much faster are we talking?
We're talking up to 25 times faster than some previous methods.
Wow. That's significant.
It's like having a super organized workspace.
Okay.
Where everything you need is right at your fingertips.
Yeah, I like that analogy. Very efficient. That's a pretty remarkable improvement.
It is.
But, I mean, speed isn't everything, right?
Yeah.
How does S2 attention affect the model's accuracy?
Right.
Especially when dealing with those long chunks of text.
That's a great question.
Yeah.
And what's fascinating is that it doesn't just speed things up.
Okay.
It actually helps LLMs perform better. On tasks involving very long sequences.
Okay.
Think about finding a single fact hidden within a massive document.
Okay.
S2 attention really shines in those scenarios.
So it's not a trade-off between speed and accuracy.
Right at all.
It's a win-win.
It seems to be.
Color me impressed. So did the researchers just simply swap out the old attention mechanism with S2 attention?
Not exactly. They found that a hybrid approach works best.
Okay.
Combining S2 attention with a bit of the traditional dense attention in certain layers gives the best balance of speed and accuracy.
Interesting.
Think of it like a marathon runner who strategically conserves energy during most of the race, but goes all out for the final sprint.
So a bit of both worlds for optimal performance.
Exactly.
I like that. Before we get into the really nitty-gritty details, I'm curious about the broader implications of this research. Sure. What could S2 attention mean for the future of LLMs?
If we connect this to the bigger picture, S2 attention could be a game changer for making LLMs more practical and accessible.
In what way?
Imagine a world where anyone with a decent computer could run these powerful models.
Oh, wow.
That's the kind of future S2 attention could help unlock.
That's a very exciting prospect. Okay, so let's shift gears a little bit and talk about the history of the research that led up to this paper.
Right.
Where did this quest for efficient attention come from? And what were some of the key milestones along the way?
The quest for efficient attention mechanisms has been a core pursuit in the transformer world from the very beginning.
Yeah.
You see, transformers have this Achilles heel. Their computational demands grow quadratically with the length of the input sequence.
So the longer the text, the more resources they need.
Exactly. And it becomes unsustainable very quickly.
Right.
So researchers realized early on that simply scaling up transformers indefinitely wasn't going to cut it.
So they had to find a smarter way.
Exactly. A lot of early effort focused on sparse attention. Remember that idea where the model focuses on only the most important parts of the text?
Yeah, like skimming a book?
Precisely. There were some clever approaches.
Like what?
Like using sliding windows to limit the model's field of view. Or creating hierarchical structures to break down long sequences into more manageable chunks.
Sounds like a good strategy on the surface.
Yeah.
But you mentioned that these approaches didn't always live up to the hype.
Yeah, there were some roadblocks.
What were the main roadblocks?
A big issue was that these sparse attention methods often clashed with how computer hardware actually works. They might look good on paper in terms of reducing calculations, but they didn't always translate into real-world speed improvements.
Interesting.
That's where a breakthrough came with flash attention. An algorithm specifically designed to optimize attention for GPU architectures.
So this was specifically built with the hardware in mind.
Exactly. It was a wake-up call, showing that you could achieve significant speed-ups. By carefully considering how data is stored and accessed in memory.
So flash attention was a turning point then.
I think so.
Shifting the focus from pure theory to a more pragmatic, hardware-aware approach.
Precisely. And S2 attention builds on that foundation, taking it a step further by intelligently dividing up the attention workload among those different attention heads.
Right. Okay, so we have this historical backdrop.
Yes.
Now, what are the specific advancements that the S2 attention paper brings to the table?
Well, one of the key insights is this idea of KV-efficient sparsity. Remember how we talked about the model needing to store the keys and values of the text it's processing?
Yeah, so it can reference back.
Exactly. Well, traditional sparse attention methods sometimes ended up requiring the model to store all those keys and values anyway.
Even though it was only paying attention to a subset.
Even if it was only attending to a small subset of them,
So it was like trying to save space by decluttering your house, but keeping all that stuff you got rid of in the garage.
That's a great analogy. Not very efficient.
Not at all.
S2 attention addresses this by making sure the model only stores the keys and values that are absolutely necessary.
So it's really being smart about what it keeps.
Exactly, leading to significant memory savings.
That makes sense.
Then there's the concept of heterogeneous context sharding, which is all about dividing the text into smaller chunks and assigning different attention heads to different chunks. This allows for more efficient processing, much like having a team of specialized experts working on different parts of a problem.
Divide and conquer seems to be the overarching theme here.
It's a powerful strategy. And S2 attention applies it in a very clever way. Another interesting point is their emphasis on union completeness. Even with this sharding approach. They realized it's important to make sure that the model as a whole has access to all the information in the text.
Right, so it doesn't lose context.
Precisely, to avoid losing crucial context.
I see.
And finally, they found that combining S2 attention with a bit of that traditional dense attention in certain layers gave the best balance of speed and accuracy. Interesting. It's like having a specialized team, but also having a few generalists who can connect the dots and provide a broader perspective.
I see. So you're saying it's this balance between specialization.
Yes.
And then having kind of like a global view.
Precisely.
It sounds like they struck a really nice balance between specialization and overall coherence.
Yes.
But did it actually work? Did S2 attention deliver on his promises?
That's the million-dollar question, isn't it?
It is.
And the answer seems to be a resounding yes.
Okay.
The researchers ran a battery of tests comparing their S2 attention models to the original slower models.
Right, as a baseline.
Exactly. The results.
Right.
Pretty remarkable.
Okay, spill the beans. What kind of performance boost are we talking about?
On standard benchmark tests, the S2 attention models matched or even exceeded the performance of the originals while being significantly faster. In some cases, they were up to 8 times faster.
Wow, that's incredible.
And remember those long context tasks we talked about?
Yeah.
Like finding that needle in a haystack of information?
Right.
S2. Attention truly excelled there.
Okay.
They tested it on a task called Needle in a Haystack, which involved retrieving a specific piece of information from a 128,000-word document.
Wait, 128,000-word document? That's enormous. How well did it do? Don't leave me hanging.
The model achieved perfect retrieval performance.
Perfect.
Wow.
That's incredible. Finding a specific piece of information in a document that massive.
It's pretty amazing.
It's mind-boggling.
Yeah.
You mentioned earlier that S2 attention achieves these speed-ups by being very aware of how computer hardware works.
Right.
Can you unpack that a bit more for me? What's happening at the hardware level that makes this all possible?
This is where we get into the nitty-gritty of computer architecture.
All right, let's get into it.
At a high level, S2 attention is all about reducing the amount of data that needs to be moved around in memory. Modern GPUs, the workhorses of deep learning, have a complex memory hierarchy.
Right.
Traditional attention mechanisms often end up moving a lot of data back and forth between different levels of memory, and that creates a bottleneck.
So it's slowing things down.
It's like rush hour traffic on a data highway.
I like that. So it's a traffic jam, essentially.
Exactly.
So you're saying S2 attention is like a traffic management system?
Yeah.
Optimizing the flow of data to prevent those bottlenecks.
Precisely. It minimizes data movement by carefully dividing up the attention workload and keeping track of which data is needed where.
So it's very organized.
It's all about organization and efficiency. It's also designed to exploit data locality, keeping the data needed for a particular calculation as close together as possible in memory.
Right, so it's not having to go search for things all over the place.
Exactly. This reduces the time it takes to access that data. Think of it like having all the ingredients for a recipe right there on the counter. Instead of scattered all over the kitchen.
I like that analogy. It makes sense. So it's not just about doing less work.
Right.
It's about doing the work in a smarter, more organized way.
Exactly. And on top of that, it improves parallelism by breaking down the attention calculations into smaller chunks that can be processed independently. This allows the GPU to utilize its parallel processing capabilities more effectively.
So it's taking advantage of the fact that these GPUs can do multiple things at once.
It's like having a team of cooks working in parallel to prepare a complex meal.
So there's a lot of coordination happening.
There is.
Behind the scenes to make everything run smoothly.
It's like conducting an orchestra of data movement and computation. All optimized for the specific hardware it's running on. And it's this deep understanding of hardware that allows S2 attention to achieve those remarkable speed-ups.
So we've got a good handle on the problem, the solution, and the historical context. Now let's shift gears into our novel notions segment.
All right, let's do it.
This is where we take the core ideas from S2 attention and brainstorm some wild but potentially groundbreaking research directions.
Sounds fun.
You ready to get those creative juices flowing?
Always up for a good brainstorming session.
All right, so let's start with this. S2 attention excels at handling long sequences of text. What if we could apply those same principles to other types of data?
Interesting.
Like time series or even images.
Interesting thought. Time series data. Like stock prices or sensor readings.
Right.
Definitely has a sequential nature. Just like text.
Exactly.
And you could argue that images have a kind of spatial sequence. With pixels arranged in a grid.
Precisely. Instead of chunks of text. What if we had S2 attention working on chunks of time series data? Or chunks of an image?
I see the potential. For time series, we could divide the data into windows of time, like days or weeks, and have different attention heads focus on different windows. It's like having a team of financial analysts, each specializing in a different time period of the market.
I like that. And for Images.
We could break the image down into patches.
Okay.
And have the attention heads specialize in different regions.
Yeah.
Like a team of art historians.
Right.
Analyzing different sections of a painting.
That's a really neat analogy. Are there challenges in applying S2 attention to these different data types?
Definitely.
Like what?
Time series data often has complex temporal dependencies that might be tricky to capture with this kind of sharding approach.
Okay.
And images have a lot of spatial information encoded in the relationships between neighboring pixels.
Okay.
We'd need to make sure S2 attention could handle those nuances effectively.
I see your point.
Yeah.
But maybe those challenges are what make this a worthwhile research direction. Who knows what we might discover by trying to adapt S2 attention to these new domains.
I like your thinking. It's all about pushing the boundaries.
Yeah.
Who knows, maybe we'll uncover some fundamental principles about how attention works across different types of data.
Yeah, it would be very interesting. Yeah. Okay, so that's one intriguing avenue. But I have another idea brewing.
Okay, hit me.
So you mentioned earlier that S2 attention could help democratize access to LLMs.
Right.
By reducing resource requirements.
Yeah.
But even with these improvements, they still need a good deal of computational power.
They do.
What if we push this efficiency drive even further?
Okay.
What if we could make LLMs so efficient that they could run on everyday devices?
Wow.
Like smartphones or even tiny embedded systems.
Now that's a bold vision.
Right.
Imagine AI assistants right in our pockets.
Yeah.
Or AI-powered sensors embedded in everyday objects, constantly learning and adapting.
It would be a paradigm shift. It would truly make AI accessible to everyone.
Yeah.
Regardless of their computational resources.
Hold on, let's not get too carried away just yet.
Okay, fair.
To reach that level of efficiency, we'd need some radical breakthroughs.
Okay.
We're talking about rethinking how we design these models from the ground up.
Okay.
Exploring entirely new architectures, algorithms, and even hardware platforms.
I hear you. But remember, this is novel notions.
True.
It's all about exploring those what ifs.
Right.
No matter how out there they might seem.
Fair enough. And who knows?
Yeah.
Maybe what seems impossible today will be commonplace tomorrow.
Yeah.
The field of AI is moving at warp speed.
Absolutely. Okay. Let's cap off novel notions with one final, slightly more grounded idea.
Okay.
What if we combined the ideas of S2 attention and evolutionary algorithms?
Where are you going with this? I'm intrigued.
What if we could create a system that automatically discovers the optimal sparsity patterns for different tasks and hardware platforms?
Wait, so instead of manually designing those sparsity patterns, which can be a real headache, we let an evolutionary algorithm handle the heavy lifting.
Exactly. Imagine starting with a population of different sparsity patterns.
Okay.
And then using an evolutionary algorithm to select the ones that perform best on a given task. Taking into account the specific hardware being used.
Okay, yeah.
The algorithm could then breed new patterns.
Oh, I like that.
By combining and mutating the most successful ones, gradually evolving towards the optimal solution.
It's like having a team of AI-powered sparsity breeders.
I like that, yeah.
Constantly experimenting and evolving to find the most efficient way to distribute attention. I love it.
And the beauty of it is that the evolutionary algorithm wouldn't just consider the model's performance, but also the computational cost and memory usage.
It would be like a multi-objective optimization problem. Yeah. Balancing accuracy, efficiency, and maybe even other factors.
Yeah, imagine telling your AI system, run this language model on my smartphone. And it figures out the most efficient way to do it automatically.
Wow.
Without any manual tweaking.
That would be amazing. True plug-and-play AI tailored to whatever device you're using.
Okay, I think we've had a good brainstorming session with novel notions for today.
I agree. That was fun.
It's been fun to let our imaginations run wild.
Yeah.
But now let's bring it back down to earth and reflect on what we've learned about S2 attention.
It's a really elegant approach to tackling the efficiency challenges of transformers, and I think it has the potential to significantly impact the field of AI.
Yeah.
What stands out to me is how it bridges that gap between theoretical advancements and practical considerations.
Right. It's not just about algorithms that look good on paper.
Right.
It's about making them work in the real world on real hardware.
Exactly. They've shown that you can achieve significant performance gains by truly understanding the hardware you're working with.
Okay, so what's the bottom line for our listeners? What should they take away from this deep dive into S2 attention?
Here are a few key takeaways.
Okay.
Efficiency matters.
Yeah.
As AI models continue to grow in complexity, finding ways to make them more efficient is absolutely crucial.
Right.
And it's not just about saving money or resources.
Right.
It's about making AI accessible to a wider range of people and applications.
That's a really good point, yeah.
Hardware awareness is key. Optimizing algorithms for the specific hardware they'll be running on can lead to game-changing performance improvements.
Okay.
And thinking outside the box is essential.
Yeah.
Don't be afraid to challenge conventional wisdom and explore unconventional approaches. That's often where the real breakthroughs happen.
Excellent points. Remember, the link to the S2 attention paper is in the show notes. If you want to dig deeper into the technical details,
highly recommend it.
So that brings us to the end of this deep dive into the fascinating world of S2 attention.
It's been a pleasure.
We hope you found it informative, engaging, and maybe even a little inspiring.
Until next time, keep those minds curious, those algorithms efficient, and those imaginations firing on all cylinders.
And remember, the most important thing is to never stop learning, exploring, and questioning.
Well said. Until next time.
Until next time.
And the answer seems to be a resounding yes.
Okay, good.
The researchers ran a battery of tests comparing their S2 attention models to the original, slower models.
Right, as a baseline.
Exactly, and the results. Pretty remarkable.
Okay, spill the beans. What kind of performance boost are we talking about?
On standard benchmark tests, the S2 attention models matched or even exceeded the performance of the originals while being significantly faster.
Okay.
In some cases, they were up to 8 times faster.
Wow, that's incredible.
And remember those long context tasks we talked about?
Yeah.
Like finding that needle in a haystack of information?
Right.
S2 attention truly excelled there.
Okay.
They tested it on a task called needle in a haystack. Which involved retrieving a specific piece of information from a 128,000-word document.
Wait, 128,000-word document? That's enormous. How well did it do? Don't leave me hanging.
The model achieved perfect retrieval performance.
Perfect.
Wow, that's incredible. Finding a specific piece of information in a document that massive.
It's pretty amazing.
It's mind-boggling. You mentioned earlier that S2 attention achieves these speed-ups by being very aware of how computer hardware works.
Right.
Can you unpack that a bit more for me? What's happening at the hardware level that makes this all possible?
This is where we get into the nitty-gritty of computer architecture.
All right, let's get into it.
At a high level, S2 attention is all about reducing the amount of data that needs to be moved around in memory.
Modern GPUs, the workhorses of deep learning, have a complex memory hierarchy.
Right.
Traditional attention mechanisms often end up moving a lot of data back and forth between different levels of memory, and that creates a bottleneck.
So it's slowing things down.
It's like rush hour traffic on a data highway.
I like that. So it's a traffic jam, essentially.
Exactly.
So you're saying S2 attention is like a traffic management system, optimizing the flow of data to prevent those bottlenecks.
Precisely. It minimizes data movement by carefully dividing up the attention workload and keeping track of which data is needed where.
So it's very organized.
It's all about organization and efficiency. It's also designed to exploit data locality, keeping the data needed for a particular calculation as close together as possible in memory.
Right, so it's not having to go search for things all over the place.
Exactly. This reduces the time it takes to access that data.
Okay.
Think of it like having all the ingredients for a recipe right there on the counter. Okay.
Instead of scattered all over the kitchen.
I like that analogy. It makes sense. So it's not just about doing less work. It's about doing the work in a smarter, more organized way.
Exactly. And on top of that, it improves parallelism. By breaking down the attention calculations into smaller chunks that can be processed independently. This allows the GPU to utilize its parallel processing capabilities more effectively.
So it's taking advantage of the fact that these GPUs can do multiple things at once.
It's like having a team of cooks working in parallel to prepare a complex meal.
So there's a lot of coordination happening.
There is.
Behind the scenes to make everything run smoothly.
They're conducting an orchestra of data movement and computation.
All right.
All optimized for the specific hardware it's running on.
Yeah.
And it's this deep understanding of hardware that allows S2 attention to achieve those remarkable speedups.
Okay, so we've got a good handle on the problem, the solution, and the historical context.
Now let's shift gears into our novel notions segment.
All right, let's do it.
This is where we take the core ideas from S2 attention and brainstorm some wild but potentially groundbreaking research directions.
Sounds fun.
You ready to get those creative juices flowing?
Always up for a good brainstorming session. It's been a fascinating exploration of S2 attention. It's not every day you come across a paper that's so elegantly crafted.
Yeah.
Both in terms of the core ideas and the way they've been validated through experiments.
I completely agree. And, thinking about all this,
it
strikes me that we often talk about efficiency in AI.
Right.
As if it's just about making things faster or cheaper.
That's true. We often focus on the practical benefits, which are undoubtedly important.
But what if we viewed efficiency as something more fundamental?
Okay.
Something that's deeply intertwined with the very nature of intelligence itself.
That's an interesting perspective. Are you suggesting that intelligence, whether natural or artificial, inherently seeks efficiency?
Exactly. Think about biological systems.
Okay.
They've evolved over millions of years to be incredibly efficient in terms of energy consumption and resource utilization.
And the human brain, despite its remarkable computational power, operates on a surprisingly modest amount of energy.
Precisely.
Yeah.
So perhaps this drive for efficiency isn't just a pragmatic concern, but a fundamental principle that shapes the development of both biological and artificial intelligence.
That's a profound thought. It suggests that as we strive to create more intelligent AI systems, we need to pay close attention to how efficiently they use resources.
And maybe that's one of the key takeaways from this deep dive into S2 attention. It's not just about making transformers faster. It's about pushing the boundaries of what's possible in terms of efficient computation, which might be a key ingredient in unlocking even higher levels of artificial intelligence.
I love that insight. It's a reminder that even as we celebrate these incredible advancements in AI, we need to keep asking those fundamental questions about the nature of intelligence itself.
Absolutely. Well, on that note, I think we've reached the end of our deep dive into the world of S2 attention.
Yes.
We hope you found this exploration informative, insightful, and maybe even a little bit mind-bending.
If this conversation sparks some new ideas or challenged your assumptions about the future of AI, then we've accomplished our goal.
As always, we encourage you to dive into the research yourself.
Yes.
Explore these ideas further, and maybe even come up with some novel notions of your own.
Who knows, you might just spark the next revolution in AI. Until next time, stay curious, stay engaged, and keep pushing the boundaries of what's possible.
And remember, the most important thing is to never stop learning, exploring, and questioning.
Well said. Until next time.
Until next time.